All right, so hopefully that will record. We'll see how that goes. Okay, so right now we're all in the view where you guys can see me. In a second, I'm going to share my screen with you. I do ask that while we're chatting, unless it's very quiet where you are, that you mute yourself. And then you can kind of unmute yourself as you have questions and things that come up. So feel free to talk, but only just because it eliminates some of the background noise for the rest of the people listening, plus for the recording. So, okay, cool. And whenever anybody else joins, no big deal. We'll just pop back up. We'll say hi to them, and then we'll jump back over.
Here.
Oh, hello. Welcome.
Can't hear you, Maria.
We can't hear you, but we can see you. You have yourself muted.
Here.
Okay,
so sorry.
Oh, no worries. No worries. We're just getting going. So, all right, cool. So in a second, like I said, I'm going to share my screen with you guys. We're going to cover 7.1 and 7.2. And so that's kind of our agenda for this morning. So let me figure out sharing my screen here. Let me get that together.
I'll be right back.
Okay. All right, let me know. Can you see that change? Are you able to see my screen at this point?
No, I just see you.
You just see me. Okay, let me try it again. Oh, I know what I'm going to do. Oh, okay.
Good.
Yeah, I don't know why it does that. It's really weird and it kind of freaks me out. Okay. Where was I here? So, all right. So now can you see my screen? Can you guys see my screen?
Yes.
Yes. Yes.
Perfect.
See you. See a screen.
We're all muted.
I know, we're all muted.
Yes. No, but can you actually see my screen or can you see me?
I can see the screen.
Okay. Okay. All right, so I'm just moseying down here. Although I had already downloaded these, I don't know where they went on me, so I'm just gonna re-grab them here. Oh, they're there. Okay. All right, so this 7.1 just has a couple of slides, kind of like the other chapters have, but we'll run through it really quick. So this chapter is really on estimates and sample sizes. So what we're going to learn is we're going to learn how to use some of the things that we've seen kind of cumulatively through the course to be able to estimate some things about the population from the information we have from the samples. So we're going to cover, like I said, 7.2, which is on estimating a population proportion, which is essentially a probability, using our sample proportion. So that's kind of where we're going. And we're also going to learn how to calculate how big of a sample size we should have. So I know we've been kind of assuming that any size sample is fine through the purposes of the course so far, and for the most part, the problems that we've been going over, they actually just pick the sample size for us. But there is actually a way to determine what the appropriate sample size is based on the size of the population. So we're going to look at some of that as well. Okay. So in chapters 2 and 3, we use descriptive statistics when we kind of summarize data. So we use graphs and some tables, and we learned about means and standard deviations and all of that kind of stuff. In chapter 6, we talked about critical values. Now, we didn't get into talking a ton about critical values when we actually met. We briefly discussed it, but I'm going to kind of walk you back through what a critical value is. Essentially, it's just a z-score. That's really all a critical value is. It's just a slightly different format. So the way that this critical value is actually noted is this z with kind of a subscript of this symbol. And that symbol is actually your probability or proportion symbol. So basically, the way that the notation works is just like before. Like before, we had been given like a percentage or a like 2.5% from the end, or we had been given a z-score. Here, what we basically do is this symbol, unlike how the z-scores are actually read, which is always the area to the left, these are actually read as the area to the right. So it's a little bit different, but we'll see this a little bit when we get more into the material. But how you would note, so if that symbol, which again indicates the area to the right of your z-score, but it is a probability or a proportion, just like what we saw in chapter 6. So say that was 0.025, the critical value would be the z that you find at that 0.025. And you would just look that up on your z-score table the same way that we have before. You'd go to 0.025 in the center of your z-score table, and you'd find that that corresponds with a z of 1.96. So basically, that's the critical value. The critical value, this z with the subscript of 0.025, equals 1.96. And that translates into having an area to the right of that 0.25. So we're going to talk a little bit more about that, but that's some of the things that we're going to be using for this next section. So I'm not going to talk a lot about this preview because we're not doing some of this. What we're really, I jumped out of the slide, but what we're really going to focus on again is those population proportions, so population probabilities, and translating those from sample probabilities. Okay, so bear with me for one moment. I'm going to go grab the next set of slides that we need. Okay. All right. All right, so this is really where we're going to spend our time in Chapter 7. So this is on estimating a population proportion. And like I said, we're going to use information that we've already learned how to use from the samples to be able to estimate some things about our populations. All right, so the key concept in this section is that we're going to look at methods for using a sample proportion. And again, a proportion is the same thing as a probability to estimate the value of a population proportion. And we've talked throughout the class about the relationship between populations and samples, and that a sample is taken from the population, and if done correctly, it should represent and help you understand something about your population. And we're going to kind of put that to the test here in this section. So we're going to learn about how a sample proportion or probability is the best, what they call point estimate of the population proportion. And we'll find that what that basically means is that the sample proportion can be used as the population proportion, that for the purposes of this section, they are seen as equivalent. We're going to learn about how we can use a sample proportion to construct what we call a confidence interval. And I'll tell you more about what a confidence interval is soon, but basically it gives you an idea of how confident you are that you've captured something about your data. And there's different ways to go about that, and we're going to learn that in this chapter. And so we're going to construct a confidence interval and use that to estimate the true value of your population proportion. So we're going to first, like I said, use the sample proportions to basically get an estimate of the population proportion. Then we're going to use confidence intervals to understand whether or not that sample proportion is really a good estimate of that population proportion. And then we're going to learn how to find the correct sample size needed to estimate a population proportion. So those are really our three main topics we're going to discuss this morning. Okay, so the definition of a point estimate. It's a single value used to approximate a population parameter. So what I mean by that is basically you're going to use something that you've already have a value for from your sample, and you're basically going to say that this is the best estimate I have of my population for whatever that parameter happens to be. In this particular section, we're dealing with proportions or probabilities, but in 7.3, if we were covering that, we would see that you can also use a sample mean and a sample standard deviation to make estimates about the population as well. So that's why they call it a population parameter, because it could be any of those things. It could be the probability, the mean, the standard deviation. But again, in this particular section, we're only going to focus on that proportion or probability. So here's a little bit of some notation for you. So the sample proportion is actually, the symbol for it is what I call p hat. So it's basically a lowercase p with a little hat on the top. And the population proportion the population proportion, in contrast with the sample proportion, its symbol would be the lowercase p by itself without the hat. So again, sample proportion is kind of p hat, and population proportion is just p. And what this slide is telling us is that the sample proportion is the best estimate we have for the population proportion. So I think they show you, no, they don't show it to you. But basically, you can almost assume that p hat equals p for the purposes of an estimate. Now, it is just an estimate, meaning that it's not 100% accurate, but it should get us in the right ballpark, and that's why it's able to be used this way. Okay, so let's look at an example of this. So the Pew Research Center conducted a survey of 1,007 adults and found that 85% of them know what Twitter is. Okay, and we're told that the best point estimate of P, which is the population proportion, is the sample proportion. Now, this is where it gets back into, because you're probably wondering, how did they figure out that this P hat equals 0.85? Well, remember from I believe it was in chapter 5, when we did binomial equations, we had lowercase p and lowercase q. And lowercase p was meant to represent our probability of success, and lowercase q was our probability of failure. And that we learned that if we subtracted, that the two together must equal 1. And so if you're given your probability of success, you're able to find your probability of failure by subtracting that number from 1. And so this p hat is that probability of success. Although it's called something a little bit different here. Now it's called p hat, not just p. But really, they're found the same way. So just like we're told, and this is actually an example from chapter 5. I don't know if you guys remember this one, but we actually did a Twitter example in that section. And so that 85% is our probability of success. 85% of the people that were surveyed knew what Twitter was. And so we can use that same logic here. So our p hat is also that 0.85. And if we had q hat, so essentially our probability of failure, that would be 0.15, which is the difference between from when you subtract this from 1. So I don't know if everybody's with me up to this point. So how are people feeling up to here?
I'm lost on Q hat.
Okay, so it's just a symbol. Don't let it confuse you. Basically, they make a relationship between p hat and p. So p hat is your sample proportion, and p is your population proportion.
Right.
So what they've had to do here is, because if they called this one p as well without the hat, you'd basically have your sample that would also have a p, and your population would also be represented by a p. So they had to distinguish between the two, and so they gave this one a little hat. But, so that's your sample proportion, but that is also the same thing as what we saw in chapter 5 for your probability of success. And so what you're going to see in the equations here is we're going to see p hat, which is, again, the same thing as your sample proportion, but it's also the same thing as your probability of success. And we're going to see q hat, which is our probability of failure.
Q is failure.
You know, I'm not sure if anybody else has seen this. I just see a blank screen. Are you showing us a screen?
Yeah, I am.
Oh yeah, I see a screen.
I see a screen.
You may need to if yours is giving you trouble, I would say
I don't know what I'm doing here.
exit out of the call and rejoin. And I'm not sure if maybe
Lost it.
yeah, maybe it just lost the connection to the screen sharing. Go ahead and try that and see and let us know when you're back in.
Log out.
Yeah, just log out and log back in.
So, Stacy, question. This is Nicole. I guess what this whole section is. What's it basically about? What are we trying to figure out? Maybe I don't understand what you're saying.
So we've been talking about samples up to this point. We've been saying that we can take information about our samples and that information should reflect our population. And here we're kind of pulling those pieces together. So we're pulling together what we've learned up to this point and saying that this sample proportion, which is, again, is what we've been looking at all along. We've been looking at samples, and all a sample proportion is a sample probability. That's all it is. And we're saying that sample proportion can be used as an estimate of our population proportion. And so there's a direct relationship between p hat, which is our sample proportion, and p, which is our population proportion. That's new what we've seen this section. But if you go back to chapter 5, we learned about P and Q when we did binomial equations. We talked about P being the probability of success and Q being the probability of failure. And so this P that you're actually seeing here, it's definitely your sample proportion. It's a probability, but it's also the same thing as your probability of success. Because in the problems, we're going to be given our probability of success. And we're going to need that to be able to, that will be our p hat that we will use in our equations, as we're going to see. So just think of this as an extension of what we kind of learned in chapter 5 with P and Q, except now they're p hat and q hat. Other than that, they mean the same thing that they did in chapter 5.
Okay, thank you.
You're welcome. So we'll give Marianne a second to see if she can get back in.
I'm here. Do you see me?
I can see you. Can you see the screen?
Yeah.
Okay, so this time you can see the lecture? Okay. All right, good. All right, let's keep going. So this was, so we're kind of in the middle of an example here. So just to reiterate again, so this p hat is our sample proportion. Proportion, don't let that word throw you off. All a proportion is a probability. A proportion is really just telling you how big the slice of the pie is, and that's the same thing that a probability does. So, so again, this is equivalent to sample probability. But for the purposes of this section, they call it proportion. So just understand that those two terms are used interchangeably. So this p hat is our sample proportion, and it's equal to 0.85 because that's the probability of success that we were given in the original problem. This 0.85, or 85% likelihood of them being successful in knowing what Twitter is. All right. So we need to talk about what a confidence interval is, because this is actually one of the, basically they're going to set the stage for a number of things, and then we're going to learn how to do all the different calculations. So a confidence interval is basically, let me back up. So if I were to take this 0.85, this probability of success for our sample proportion, and say that it's equal to our population proportion, you know, we're using it as an estimate, but we don't really know exactly whether that is true or not. And so confidence intervals are used. And a confidence interval is basically where you say, I want to be 95% confident that my sample proportion equals my population proportion. I want to be 99% confident. And when you see studies like that, and I'm sure you have, most studies are based on a 95% confidence interval. That's the most common one used. You'll also notice that on your z-score table, down on the very, very bottom of the z-score table, it actually gives you the 95% confidence interval. I think it gives you 90, 95, and 99. And that's because those are the most commonly used ones. So people like to be 95% confident. And the reason why, like we've talked about kind of this notion of 5% and 95% before. We've said that something that's 95 or 5% or less is very unlikely, and something that 95% or greater is very likely. And so 95% is sort of that cutoff where mathematically they've determined that they can be confident in something. And so that's kind of where that comes from. Okay, so let's talk about confidence intervals. So confidence intervals are basically a range of values that are used to estimate the true value of the population parameter. In this case, the parameter that we're looking at is the population proportion. And we're gonna learn about this and see more of it, so just bear with me. This is just the definition. And a confidence interval is usually abbreviated as CI. So if you see anything that says CI equals, that's confidence interval. That's what that stands for. Okay. So the way that a confidence interval is actually calculated. So you basically have what you call a confidence level. And that is basically a probability. It is the probability 1 minus your area to the right, which is what we said this little symbol means. We talked about that back, let's see. Oh, it was in it was in that little part we saw in 7.1. Sorry about that. But basically, as we'll see, this looks a lot more complicated than it really is, so bear with me for a minute. There's 3 common values for that symbol. There'll be 0.10, which is a 10% to the right. There'll be 0.05, which is 95% to the right. And there will be this 0.01. And those correspond with this 90%, 95%, or 99%. So if I have a 90% confidence interval that I want to do, I would have 1 minus this 0.10. And when you do 1 minus that, it's 0.9, which is where that 90% comes from. Same thing here. If I have a 95% confidence interval, my value here is 0.05. 1 minus 0.05 is 95, or 0.95. And the same thing goes from here. If you have a 99% confidence interval, your value is 0.01, and it's going to be 1 minus that 0.01, and that's where the 99% comes from. We're only going to be using these 3 sets of values. So you're not going to have the whole table like we saw before up for grabs. Essentially, these are the most common choices, and these are the choices that we will see over in this section and that you'll see in my math lab. So, so basically what happens is that a confidence level will be selected in the problem. It'll tell us we're going to have a 95% confidence level, or we're going to have a 99% confidence. And then based on that, we know which of these numbers we need to plug into our equation, as we will see. So I know this looks very wordy and complicated, but it's actually pretty straightforward once you actually look at how it's done mathematically. So just bear with me for a couple of minutes, and then if there's questions, I'll clear it up. Let's see. I don't know why they do it like this. I'm trying to... Unfortunately, this section is super, super wordy. That's why there's 40 slides. So there's going to be places where we're going to talk a lot and then finally see an example. And this is one of those where there's a bunch of slides and then they finally will show you how to actually do the calculation for the confidence interval. So just bear with me as we keep going. So how do we actually interpret a confidence interval once we calculate one? So it's important that they're calculated correctly. The challenge here is I don't like how they've done this here. Let me see if I can get to an example, and then we'll back up. I really don't like how they've done this. Yeah, they're not making this easy for me. Okay, well then I guess we're just going to have to keep going. But basically, the way a confidence interval winds up getting expressed is that it's basically a range. So you're going to have kind of like what we've seen, although a different concept, but just to try to give you to make it more concrete. Just like in range rule of thumb, how we wound up with a maximum value that fit and a minimum value that fit. That's essentially kind of how a confidence interval gets constructed, kind of like you'll see here. So if P, this P being our population proportion, and this is actually building off of this example that we already saw, this 85% of Twitter. So we said that P hat, which is our sample proportion, is 0.85, and that is the best estimate we have of P, which is our population proportion. So keep that in mind as we look at this. So when they didn't show us how they calculated the confidence interval here, but they're telling us that the confidence interval at 95% for the population proportion is between 0.828 and 872. So keep in mind that the sample proportion, P hat, that we saw was 0.85. And we were told that 0.85 is a good estimate, but that it's not entirely accurate. When a confidence interval is actually constructed, you find that the range for your population proportion is really between 0.82, so 82%, and 87%. So that 85% got us in the ballpark, right? The population P hat, your sample proportion, got us in the right ballpark. It's pretty close. It fits within this interval. But what we're saying is that the population, because it's a little more dynamic than that, we can't say that 0.85 is the exact right answer for it. So instead, we come up with the range, and we say that between this range, we are 95% confident that it contains the true value of the population proportion. So essentially, we're saying that 0.85 is a good estimate, and that this range, we're 95% confident that the true value is somewhere in between there. So that means that if we were to select a different sample of the same thing, that we should be able to get that. Don't worry about this. It's just going to make things more confusing. These last two parts here, just don't worry about those. Focus on what I've had to say up here, and we're going to see this in examples. So I apologize that the way that they've set this up makes it a little bit abstract for the moment. But the bottom line is that this confidence interval, it's going to give us an estimate of where the true value of the population proportion falls based on what we found for that sample proportion. All right, what questions are there so far on this? I know, like I said, it's very abstract right now. Anything? Okay, well then I'll keep going then. Okay. Don't worry too much about this. You're not really going to be dealing with overlapping confidence intervals and things like that. The bottom line is that you want to be sure when you're looking at a confidence interval that you understand what it's saying, but that's what this caution is. Don't worry too much about this though, because you're not going to see any where we're going to have multiple data sets or things like that. Okay. The reason why we do confidence intervals, just so that you understand the kind of where this builds in the future for stats, and I know that none of you are taking stats too, but just like in science, you can have hypothesis testing where you basically say, well, I think the sky is blue because of X, Y, and Z, and that's your hypothesis. You can do the same thing in math. You can set up a mathematical hypothesis. And so these confidence intervals are used later for hypothesis testing. Now, we're not going to get into hypothesis testing. That's what chapter 8 is really on, and we decided that we were cutting 8. So we're never really going to see that piece, but just understand that that's why they teach confidence intervals here in chapter 7, is because it helps create the building blocks that you need for hypothesis testing later on. Okay. All right, so now that we've talked about all of those things, let's back up and talk about some things that we saw in chapter 5 that are related to this section. So in chapter 5, we talked about binomial probability distributions, and we learned about, oh no, I'm sorry. I'm confusing my chapters here. Yes, in chapter 5, we definitely did learn about binomials. That's where we got our p hat, or our p and our q, which now we've said is p hat and q hat. And then in chapter 6, we talked about z-scores. And so we learned that you can take a z-score, and that z-score represents and can be used on our table as long as you're dealing with a standard normal distribution. And in chapter 6, we played around with a whole bunch of different z-scores and different values. And so basically, just like in what we've talked about in other places in the course, you can have z-scores that are likely to occur and those that are unlikely to occur. So we've hinted about this 95% 5% kind of cutoff. That anything that's 95% or greater is likely to occur, and anything that is 5% or lower is unlikely to occur. And that same thing can be applied to z-scores, and we call that a critical value. And so basically, critical values are kind of set the stage for things that separate what's likely to occur from what's unlikely to occur. And we kind of just touched on this when we talked in chapter 6. So we need to kind of back up a little bit and make sure that we know how to use critical values. So what they tell us here is that critical values are based on the following two things: that under certain conditions, the sample distribution of a sample proportion can be approximated by a normal distribution. What that means is that that your sample proportion should follow that bell-shaped curve, like we've seen in other places. That's what they mean by a normal distribution. So don't worry too much about that. That's sort of a given. And that the z-score that's associated with that sample proportion has a probability of this symbol here, this little guy, divided by 2, of falling in the right-hand tail. So what I mean by that is, when we've been so far up to this point, when we've looked up a z-score, it's always been, and most of the time, the area that we've been interested in has been the area to the left. And with critical values, the critical value actually represents that area to the right. And so it's a way of kind of talking about how likely something is to occur from something that's not. This will make more sense when like I said, when we get off of all of these endless words and start to actually look at the math. So just bear with me for a minute, but understand that a z-score has an associated critical value with it. And that critical value is meant to help you determine whether something is likely or unlikely to happen, as we'll see. So this is kind of a little diagram of what this looks like. So basically, this Z here with the symbol, this subscript, what that is that's the critical value. And it's basically the borderline that separates, if you imagine that this border separates values that are highly likely to have happened, so anything that's up here is going to be 90, like, for instance, 95% or greater chance of having it happen. Whereas things down here would be your 5% or less. And so it's really meant to kind of show you the break between those two. So it's kind of similar to things we've seen in the past, but kind of getting in a little more specific here. And as we're going to see, there's only 3 critical values we'll be dealing with. And I mentioned them back, let's see, where was I? Back here. These 3 here. So we're really only going to be using 3 critical values, this 0.1, 0.05, and 0.01, as we'll see. And those will correspond with confidence intervals of either 95% or 90%, 95, or 99%. And again, I apologize for all these words. It's a little confusing until we actually get into the examples. Okay, so again, the critical value is the number on the borderline that separates statistics that are likely to occur from those that are not likely to occur, and that this symbol here represents that area to the right, as we'll see. Okay, so here's like a little example just to help make things make more sense. And like I said, I apologize. This is one of the reasons I don't typically teach Chapter 7 when in my undergrad class, because I don't feel like the book lays it out very well. I feel like it's a little bit confusing. So I apologize again that this section is a little bit crazy, but if you bear with me, it'll make sense. Okay, so let me kind of walk you through here what we're looking at here. So when you have a confidence level of 95%, it means that you're 95% confident, which is everything that's in this section in the blue, which means that what's left is 5% being non-confident, right? That if in here you're confident, out here you're not confident. And if the whole graph, like we've seen in other sections, has to be 100%, and if this whole middle is 95%, it means what you're left with is 5%. And that 5%, when you divide it by 2, which is essentially what they're doing with this symbol here, means that you wind up with 0.025 on this end and 0.025 on this end. And when you look up 0.025 on our z-score table, you would see that it corresponds with a z-score of negative 1.96. And as we saw in Chapter 6, as long as they're symmetrical, you can just change the sign and that represents your other. So essentially your critical values here are negative 1.96 and 1.96. And those are the boundaries that separate what's likely to have happen from what's not likely to have happen. All right. People, feel free to unmute and ask me any questions that you have now that I've kind of shown it to you in more of a mathematical way here. Anybody?
I don't have any questions.
So what we're looking for is that like small black line in between the blue and red.
Yeah, so this line here is where that critical value falls. And in Chapter 6, we sort of talked about, like I said, we talked about z-scores specifically. And really all this is a modified z-score that just tells you that the area, it's almost like a z that's telling you the area that you're going to look up on the table. It's kind of connecting the two pieces together. So really how this would look is it would be negative, like this one here would be negative z, and then this symbol would be plugged in for this value. So it would be negative z with a subscript of 0.025. And when you look up that 0.025 on your z-score table, you find that it corresponds with this negative 1.96.
Okay, so if we get like a word problem, are we to find the 0.025?
Usually, as you're going to see, they're going to tell you a confidence interval. They're going to say,
Okay.
You're going to use a 95% confidence interval. Okay, well in that case, there's 5% then that you're not confident. You'll divide that by 2, and then that will give you your critical value on either side. If you had a 90% confidence interval, you'd have 10%, and you divide that by 2, and you'd have 0.5 and 0.5 on either side. And if you had a 99% confidence interval, you'd have a 1% unconfident, and you'd divide that in 2. So you're only going to be dealing with these three circumstances.
Okay.
Where you're going to have
Got it.
either a 90, a 95, or a 99. And then these will be your corresponding critical values, and you'll just divide them by 2 to spread it out on either side of the graph, basically.
Okay.
All right, and it'll, like I said, it'll start to all fall into place when we do more of the examples, but this kind of gives you at least a little bit of a view of how this works. All right. So this table is the table that you want. I recommend just writing this table out for yourself, and I'm happy to give you all some time to do this. This will actually prevent you from having to go and look up anything on your z-score table, because we're only going to be dealing with these 3 sets of circumstances. So we just did 95%. So we said that if you're 95% confident, if you turned that into a decimal, that would be a 0.95 probability, right? And so the difference between that and 100% is 5%. And if you turn that into a decimal, it's this 0.05. So when you take that 0.05 and divide it by 2, you're going to get 0.0025. And when you look up that value on your table, just like what we saw here, it's going to correspond with this modified z of 1.96. If we were doing it for a 90% confidence interval, these are the numbers you would use. And if you were doing it for a 99% confidence interval, you would do it for these numbers. So this table here is really all you're going to need for plugging things in. You're just going to pull stuff right off of this table. You won't need to use your big z-score table in this section, unless you really want to, I guess. The information is certainly the same, but because we're only dealing with these 3 confidence levels, there's not really a need to use your whole table. It just makes it a little easier. Okay, does everybody got these jotted down?
I have them.
Yeah.
Yeah, I do.
All right. You know what I realized? I should probably jot them down for myself really quick too. 'Cause I just don't know all of the z-score side of it off the top of my head. So let me write these down for myself, because we're going to need these as we start solving problems.
I have a question.
Sure.
Okay, so the confidence, you take the confidence level, like 99%, you said,
Okay.
and then you minus that by 100.
Yeah.
That gives you the 1%,
Yes.
right?
Yep. That's
And
how
then
this.
you
That's where
divide
this
that
comes from.
Two?
Yep. And then you divide that in half, because you're dealing with both sides, right? If this is what you're confident,
Okay.
you have to be unconfident on either side. And so they basically spread the difference out on either side. That's where that dividing by 2 comes in. It's to send half of it over to this side and keep half of it on this side.
So when you divide by 2, that's where you get the critical value.
Well, that's where you get the value, the z. All right, let's do these out so it makes a little bit more sense. So, all right, let's say we're gonna do that 99% confidence interval, and we're gonna take that 0.01 and we're gonna divide it by 2. Okay, what you're gonna get is 0.0005. And if you were to look up that 0.005 on the z-score table, that corresponds with this value. But the table saves you the work of having to do that. You don't have to look that part up.
Oh, we don't have to look at the z-score?
No, you can just use these values right here. This is the only stuff you're going to need.
Oh, okay, so we don't have to try to figure this out then?
No.
We don't need the equation.
No, you're not going to need to figure it out. This table, basically, I'm showing you how you would go about figuring it out, but you're not going to actually have to do that. You're just going to use this table. and the values that are right on this table. I'm just giving you all the background of where these numbers come from. Okay. All right, let's keep rolling. Okay, so now we're going to get into actually calculating this out. So just, like I said, hang in there, keep all of these pieces together, and we're going to pull them all together in a couple of minutes and actually show you how to construct one of these confidence intervals. Okay, so here, and we actually learned about this a little bit in chapter 6. But when data from a simple random sample is used to estimate a population proportion, which is that P, the margin of error is denoted, which we said that denoted basically means that it's the symbol that stands for it, by E. And so that E is the maximum likely difference between the observed population, or basically between your sample proportion, so p hat, and the true value. So basically, it's basically giving you an estimate of how much error there should be between your sample proportion and your population proportion. Because like we've said, your population or your sample proportion is a good estimate of your population proportion, but it's not exact. And so there's some amount of error in there. And in order to calculate your confidence interval, you have to look at your margin of error. And I'm going to show you how you actually calculate that in a second. But just understand that it's one of the, basically in the equation that we're going to use to calculate out our confidence interval, E is one of the symbols we're going to see. And so this is just walking you through what that E actually means. So once we see it in the equations, we're going to understand what that is. So this is actually the equation for calculating out that E. So again, E is your margin of error, and it's basically a maximum amount of error. So that can, and how it's calculated is you take that critical value, so one of these guys over here in this column, that's what's going to get plugged in here. And then you're going to multiply it by the square root of p hat times q hat, so your probability of success times your probability of failure, divided by n, which is the number of trials, just like what we've seen before. And again, this symbol here is only going to have one of three values. It's going to be one of these three that we saw in our table here. Okay? And so the problem will tell us that we're going to use one of those confidence levels, and then based on that, we'll know what to plug in here. And then from the problem itself, the numbers that are given in the problem, we'll be able to fill in these other numbers that we need to calculate our margin of error. Okay, so just walking you through all the symbols again. I don't know if this is helpful or just more confusing, but these are all the symbols that we're going to see in our confidence interval equation. So we're going to see P, which is our population proportion. We're going to see P hat, which is our sample proportion. We're going to see N, which is the number of samples, like the number of trials. Same thing we've seen from N before. We're going to have E, which is our margin of error. And we're going to have our Z with our subscript here, which is going to correspond to one of these three critical values. Okay? So that's what we're going to see in our equation. All right. Oh, my goodness. They still haven't gotten to the place where we're actually getting into the equations.
Can you go back to that screen
Sure.
for a minute? So I'm just jotting it down.
Oh, yeah, no problem.
I forgot to print my my slides this week.
Oh, no problem.
Oh,
No problem.
Thank you.
All right. Just let me know when you're all set.
All set.
Okay. All right.
Thanks.
All right, so continue bearing with me, because we still yet have not gotten to the actual equations themselves. Ay, ay, ay. Again, this is why I don't usually teach this chapter, because it drives me a little bit crazy not having some solid examples and having all of these slides. So, but anyway, it is what it is. All right, so some things to know about the confidence interval itself. So we said that this confidence interval is basically going to give us a range, and it's going to tell us that the population proportion, the true population proportion, should be somewhere in that range. And just like we saw for like binomial equations and stuff, there's some criteria that has to be met in order to construct a confidence interval. And so that's actually what they're giving us in this slide. So the criteria is that the sample has to be a simple random sample. And basically what that means is that you don't really want a voluntary response sample or something like that, as we'll see. So this gets back into like things that we learned in chapters like 1 and 2. But just trust me that all the samples that you're going to be given as examples should meet this criteria. The only time that you'll need to understand to potentially use this will be if they ask you, does this meet the criteria or doesn't it? Okay, the conditions for the binomial are satisfied. So this actually, you have to have the same conditions that we saw in the binomial conditions to be satisfied, because we're using your probability of success and failure, just like we did with binomials. So just to refresh us on what those conditions for the binomials were, there had to be a fixed number of trials. The trials had to be independent. There had to be 2 categories of outcomes, success and failure, and the probability of success had to remain constant in each of the trials. So those are not new. Those are things that we saw in chapter 5. And here they tell us that there also has to be at least 5 successes and 5 failures. The reason that they say that is just to make sure that there's enough data to be able to construct the confidence interval. But again, all the problems you're going to be given are going to meet this criteria. Okay. Oh no, why? Oh, that's not good. Why are all of my slides missing their equations? That's gonna make life hard. Oh, what a mess. All right, let me get out my textbook here so I can tell you what the equations are, because clearly we're not going to be able to see them here, which is really not good. Oh, yeah. Okay. Well, hold on. I might have another way to get at this. So just bear with me for a second. I'm going to change up my screen for a minute. And I'm going to look for something on our course Canvas page. I want to see if I posted this. And if I didn't, I'm going to go post it really quick so that we have it. Bear with me for 1 second. I wonder if it's in here at all. All right, probably not. All right, I am going to add a file into our Canvas site. So I'm going to do that right now. I'm going to add it. I'll add it to this week's section. And what it is it's going to be a master formula sheet that's broken out by chapter and section. And that way you can see the equations written down better, because this a lot of the times equations don't work well in PowerPoint, which creates a lot of challenges as an instructor trying to be able to show them. So I'm just going ahead and I'm going to upload that master file so that we have it. So bear with me for a second here. I got to figure out where I have it. If I don't have it here, I'll have to go grab my flash drive. I definitely have it on there. I just don't know if I have it here on my local desktop. It doesn't look like I do. Okay, bear with me for 1 second. I will be right back. I'm just going to go grab my flash drive, and then I'll be able to upload that file that will have, it's basically a big master formula sheet so that you'll be able to see all these equations in writing. So just give me 1 second. All right, let me see if it recognizes my flash drive here. I just gotta find it. All right, there it is. Okay, so I added, everybody can still see my screen?
Yes.
Okay.
Yes.
So I added this document. I'll show it to you. And it's in the module for this week. So this is the master equation sheet. I usually don't hand it out because it's kind of confusing, and there's a lot on here. But the part that you actually need is right here. Actually, it's just really this top little part here this is the equation that isn't coming through right now. So I don't know if everybody can see this, and I know it's a little hard to see in kind of this grainy picture, but essentially the equation is p hat minus e less than symbol p, so your population proportion, greater than symbol p hat plus e. Are people able to grab that?
Yeah. Hold
Yeah. So what is that? What is that formula called?
That's the confidence interval formula.
Confidence interval.
Yep, confidence. Yep, formula.
Can you say it again? It's p hat.
P hat minus e.
Yep.
Your greater than symbol.
Yep. P.
P. Your greater than symbol again. P hat plus e.
Is that not less than?
Minus.
Well, it depends on how I guess you're looking at it. Less than or here it's it depends on which way you're approaching it in the equation,
Right,
kind of.
okay.
But yes.
So p hat minus e
Yep.
greater than p hat plus e.
Yes.
Is that correct?
Yes.
Do you hear me?
Yes.
Okay.
Yep.
Sorry.
And then the second thing that they have here, and this is the other formula you'll need, although this one came through okay on the slides that we were just looking at. This is the formula to calculate that margin of error, which is E equals your Z critical value, that weird Z, the modified Z, times the square root of P hat times Q hat divided by N. But that one came through okay in the equation. That's this formula here. What was missing is the formula that goes here. Can you guys see my screen, what I'm pointing to right now?
Yeah.
Okay.
Yep.
What that other formula is what's supposed to be right here, but for whatever reason isn't coming across properly.
I had it printed up, so I have it.
Okay, yeah. Did it print okay?
It did for me. It printed on the printer fine.
Yeah, it's frustrating because the reason why they have issues, and truthfully some of it is probably because I'm using a Mac. If you pull these like the Mac software doesn't like equations, whereas some of the PC software is a little bit better with it. So that's a good point. If you print the slides, you'll have the equations properly. They just look messed up a little bit because PowerPoint is a Microsoft program and Mac doesn't really play nice with Microsoft. It creates issues.
That makes sense.
Yeah. Really a pain in the butt.
I bet.
Okay. All right. So what the heck are they doing here? I'm just trying to see kind of where they're going. All right. I'm not sure why they have the second slide. The equation was the one I gave you up here. So, all right. So now that we have the equations, a couple of rules for rounding. Rounding should be to 3 significant digits, which is usually means significant digits is a little bit different than decimal places. The bottom line is that usually will be 2 decimal places, but sometimes it'll be 3. It depends on the number. So basically, a significant digit is anything other than a 0 usually, and so if you have a number like 2.6567, it would just be 2.65. But if you had a number like 0.615, you would keep all of those numbers. I don't know if that makes any sense, but if you're confused on significant digits, I recommend just Googling it. There's some good tutorials that'll walk you through, just like the rounding one that we sent out, that are on significant digits instead. But essentially, it's 2 or 3 decimal places is what it works out to be. All right. So now that we've actually talked about all of those things, let's actually talk about how we would construct a confidence interval now that we've talked through all the pieces of it. So this is the actual procedure for conducting or constructing a confidence interval. So first we're going to verify that all the conditions are met. So those conditions were that the sample is a simple random sample, that the conditions for the binomial are satisfied, which was the fixed number of trials, probability of success being the same in all trials, that the trials were independent, and that all of the outcomes could be classified as either success or failure. So once you can verify that all the assumptions are satisfied, which again, for all the problems you're going to be given, you can assume that is the case. The only time that you'll need to kind of remember these specifics is, big God. The only time you'll need to remember those specifics is if you're in my math lab and it's like, does this meet the equation, or which one doesn't fit? It'll be more of those types of questions. All the problems that you're going to be given, though, like actual problems with numbers, they're going to meet these criteria. Okay. So then basically, depending on the problem, they're going to tell you what confidence level that they want, 90%, 95%, or 99%. And based on that, you're going to find your critical value in the table that we saw earlier, which is this table here. So if they tell us it's 90%, we're going to know that our critical value is this, and so forth. Okay? Then we're going to actually calculate out our margin of error. So we're going to have E equals that critical value, so whatever we found on our table, multiplied by the square root of p hat times q hat divided by n. So we'll actually calculate out that margin of error. Then we're going to use those values to construct our confidence interval using the formula that we saw before, which is basically p hat minus e equal it, basically it's p hat minus e and p hat plus e. That's essentially what that formula that we were looking at on that master equation sheet works out to be. What did I do with that master equation sheet? Let me pull that back up. So that's where you need your E. So again, p hat minus E is going to give us this side, and p hat plus E is going to give us this side. And that's going to give us our interval. So it's basically going to give us a minimum and a maximum, kind of like what we saw with range rule of thumb. Although this is a different topic, it kind of is similar in some ways. So we're going to be able to construct our interval based on that. And then we're going to round, again, to 3 significant digits. So that's the whole procedure, now that we've gone through all of that. Yay! And now we finally get to an example. All right, how are people feeling up to this point?
Good.
Good? All right. All right, so let's actually do this example. So this example has 4 parts. But let's read through it first, and then we'll talk through what we need to do for each of these parts. So in the chapter problem, we noted that a Pew Research Center poll of 1,007 randomly selected adults showed that 85% of respondents know what Twitter is. The sample results are n equals 1,007 and p hat equals 0.85. So we want to find the margin of error that corresponds to a 95% confidence interval. Then we are going to actually construct our confidence interval. And then we're going to answer some questions. They want us to know, can we conclude that more than 75% of adults know what Twitter is? And that's going to be based off of our confidence interval. So we won't know the answer to that until we actually do our calculations. And then we're going to assume that we're a newspaper writer and blah, 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 blah. Okay, so let's dive into this. So the first thing that we're going to do is actually calculate that margin of error. So in order to calculate the margin of error, we need to know the different symbols that we have here. So don't pay attention to all the numbers that they've plugged in. I hate when they do this on a slide. Let's first just break down the equation. So the first thing we're going to need is our critical value. Now, our critical value is, again, going to be based on this 95% that we're being asked for in this problem. So if we go back to this table, what is our critical value going to be?
1.96.
Okay, 1.96. Great. So we know that part. All right. So we know that this part here is going to be 1.96. Our square root is our square root. We know our p hat, it was given to us in the previous slide, as 0.85. So how do we find our q hat?
Z-score table.
Nope, you don't need a z-score table for that.
1 minus.
Yep, 1 minus the 0.85. So 1 minus our probability of success gives us our probability of failure. So our probability of failure will be 0.15. And together, you can add those two numbers together and they'll always equal 1. All right. And then how about our n? What's our n?
The number of trials.
Yep, the number of trials. Okay. So when we plug all those numbers in, we plug in 1.96 for our critical value, square root, 0.85 for our p hat, 0.15 for our q hat, and 1,007 for our n, we're able to calculate out our E, which is our margin of error. And we find that our margin of error is 0.0220545. So they kept a whole bunch of numbers here. I probably wouldn't have gone quite as far as they did, but that's okay. All right, so does everybody get where we got all the numbers to calculate our margin of error?
No, I'm still calculating. Just to
Okay,
make sure
no problem.
We did the p hat and the q hat. We multiplied the p hat and the q hat.
Yep, you're going to multiply them together.
Okay.
Were you able to get it?
I forgot the square root. Yes, no, I got it.
Okay.
It's like square root. I'll say thank you.
All right. So now that we have our E and we have our P hat, we can actually construct our confidence interval. So this is what that's going to look like. Oh, now it looks fine. What? Why does it look fine here and it doesn't show up in the other slide? No idea. Okay.
It's just
Well,
temperamental.
I know, it is temperamental. Well, at least now you guys can actually see it written out rather than my grainy master formula sheet. So again, we're going to construct this 95% confidence interval, and it's already 95%. There's nothing else we need to do to get it to 95%. That was part of that E calculation that we did with our critical value. So we're going to take P hat, which was 0.85, minus our E, which was this 0.0220545. And then we're going to take that same P hat and add it. And so what we wind up with is this range, that our population proportion is greater than 0.828 and less than 0.872. So we're able to get that range.
Okay.
So for all those slides, as you can see, the math part is actually pretty easy. It's just, the margin of error equation and this one little equation. There's not really a whole lot of math, but it's all those slides explaining where all these numbers come from that makes this section a little bit cumbersome.
Excuse me.
All right, so does everybody feel good about how we constructed this confidence interval and what all the symbols meant and where we got all the numbers from?
Good, not confident.
All right, good. I'll take good.
But good.
All right, I'll take good. So you would not have a 99% confidence level at this point, but that's okay. That's okay.
No, wait.
No.
Not yet.
Possibility of that.
No, and the thing, like I said, I mean, the nice thing in this section, although, like I said, it takes them a bajillion slides to get there, is really all you need is this table, the two equations. That's really it.
Yeah.
I mean, they make it so much more complicated than it really is here.
Yeah.
Right?
They
We're on slide 28. It took 28 slides to get to this point. And frankly, I think that this is probably actually a little less complicated than some of the other things we've seen. But whatever. This is how they do it. So we're gonna roll with it. Okay. All right. So then to answer the last two parts of this question, they want to know, based on the confidence interval obtained in B, so this interval here, this 0.828 to 0.872, does it appear that more than 75% of adults know what Twitter is? Okay. So the way that we'd answer that question is, because the limits of 0.828 and 0.872 are likely to contain the true population proportion, it appears that that population proportion is a value greater than 0.75, right? So 0.75 is lower than even our lower limit. So we would say that, yes, it does appear that more than 75% of adults know what Twitter is. In fact, it looks like it's more like 83% to 87% know what Twitter is.
Mm-hmm.
Okay, so makes sense. Not too bad. And then they do this one statement that summarizes the results. So what they'd say here is that 85% of U.S. adults know what Twitter is. That percentage is based on a poll. In theory, in 95% of such polls, the percentage points... Oh, Jesus, what are they doing here? Yeah, they got into all kinds of crazy stuff here. Don't worry about D so much. I don't know why they're getting into this 2.2 percentage points. Oh, I see where their 2.2 is coming from. It's coming from 0.85 plus or minus, which is this stuff. But don't worry about that stuff too much. All right, moving on. So one of the places that you'll frequently see confidence intervals given is in analyzing polls. So Most of the time, polls are based on a 95% confidence level. So oftentimes reports don't tell you that, but that is usually what they are based on. So when analyzing a poll, these are the things that you should consider. The sample should be a sample or a simple random sample, meaning that it's not voluntary response, that you want a better way than just people volunteering to be part of it, for the purposes of this kind of polling. Don't worry about it so much as how that applies to like your projects and stuff like that. The way you've done your projects is fine, but for the purposes of this, that kind of method wouldn't work. So the confidence level will be provided. It's usually 95%, but oftentimes reports neglect to tell you what it is. But if they don't tell you, usually 95% is the default. The sample size should always be provided when you're looking at a poll, but oftentimes by media, they don't actually do that, but they should. And except for relatively rare cases, the quality of the poll results depends on the sampling method and the sample size. But the size of the population usually doesn't matter. So don't worry too much about population size. What really matters is that your sampling method is good, and that the size of the sample is a good size based on the population size. And we're going to see how to actually figure out what your sample size should be based on your population size in a minute. Okay. Some cautions they give you. Never follow the common misconception that poll results are unreliable if the sample size is small. Basically, as long as the sample size is appropriate, don't worry about the population size. And again, we're going to see how to actually go about figuring out what size is correct. Okay, so that's kind of where they're leading us to here. So suppose we want to collect sample data in order to estimate some sample proportion. The question then becomes, how many samples should we do? Oh, great. Another place where they don't give us the equation. Awesome. All right. Let me see if they give it to us. Oh, jeez. I love this. All right. Let me pull up those equations in my book so I can tell you what they actually are, because they're clearly missing. Awesome. Ay, ay. Why are they doing this to me? Why are you doing this to me? All right, because I don't think that this one is actually on that formula sheet, is it? Of course not. Of course not. Why would it be? Oh! Nope, they are here. I lied. Okay, they are very hard to see on here. So let me see if I can make this bigger. Ah, ha, ha. Okay. I know this is still very blurry. Can you guys see what I'm pointing at here? Yes? No?
Yes.
Okay, so I'm going to read you what this says, but you're going to need these top two equations. So essentially, sometimes you're going to know your P and Q, and sometimes you're not. And so there's two different equations. One is for when you know your P and Q, and one is for when you don't. So this top one is for when you don't know your P and Q. So it is N equals the critical value, that's what that is, in parentheses, squared symbol on the outside of those parentheses, times 0.25, divided by E, which is your margin of error, squared. So that's what this one is. I'm going to repeat that one more time, because I know it's kind of hard to see it actually on here. Let me see. Can I make this any bigger? No. Oh, I guess I can make it a little bit bigger. I don't know if that makes it actually any clearer, though. All right. So it's N equals, in parentheses, the critical value, that modified Z, close parentheses, squared. So you're going to square that critical value, multiplied by 0.25, divided by E squared, which is your margin of error squared. That's the first equation. Does everybody got that one?
Mm-hmm.
Okay.
Mhm.
Then the second one is for when we do know our P and Q. And the only difference is that instead of using 0.25, it's P hat times Q hat. That's plugged in for where that 0.25 is. Otherwise,
How do
the
we know
equation's
what
the
E
same.
is, the margin of error?
You would have to calculate it based on how we did it up here. It's your critical value.
Oh, geez.
Well, it's your, sorry, up here. Your critical value times the square root of P, Q, and N. But you're right. If you don't have your P and Q, it's going to be hard to get your E. So usually they'd have to give it to you. All right, so those are the two equations that we're going to be using. So let me get back to the slides here. So sorry about all these equation issues this morning, but I appreciate you guys bearing with me. So that's what would be here or what would be here. Actually, this is where if your P was known, so that second equation we looked at, that's what would go right here. And the first equation that we wrote down would go right here. That's what would be on these slides if they were working properly.
Oh.
I'm sorry,
Okay.
go back to the slide where the equation for solve for n by algebra, I think it's slide 34.
This?
Right. I'm trying to match the equation with the slide. Because I have a Mac too, so I can't see it. Like
I'm trying to figure out what this is supposed to be telling you. And because I can't see
I
it.
have my piece.
Does anybody who printed this? What equation are they? What are they showing here and here?
I have it. Hold on. Let me see.
It's E equals, no, that's not it.
Remains.
I truthfully, I mean, we can certainly have somebody who has the slides printed look at this, but this slide is not the slide that you care about. It's these two equations that you really need. Those are the only two equations you're going to need. I think what that slide is trying to show you is how we're going to use the two equations.
Okay.
Because in those two equations, you're solving for n. So that's kind of what they're talking about here, is that you're going to solve for n using these two equations. And those are the two equations that I just pulled up here. See how these are n equals and n equals? The reason being is n is your sample size, and these two equations are meant to help you figure out how big your sample size should be based on all those things that they want you to plug in. Okay. All right. So they give you a little bit of information about what you should do for the rounding here. Now, because n, basically what they say is when you wind up calculating out your n, if your n is not a whole number, you're going to round up to the next whole number, always. It doesn't matter whether the value normally would be rounded up or down, always round it up. Because think about it like this. Say that your n is the number of people you're going to sample. How are you going to sample 16.45 people? You can't. If you round down to 16, though, that's not enough people. So to err on the side of caution, you always round up, and we would round that up to 17 people. Does that make sense?
Yes.
Okay. Because again, your n, and just like when we were talking about, and not that this is the same topic, but just to kind of illustrate it, just like when we were talking about like hens laying eggs. Hens can't lay partial eggs. And n, your sample size, that can't be portions either. It has to be whole numbers, because that's the only thing that makes sense. Okay, so let's look at an example that they give us here for how we're going to actually use these equations. So many companies are interested in knowing the percentage of adults who buy clothing online. Makes sense, right?
Mm-hmm.
So they want to know how many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points. Okay, this is going to pull together a bunch of the stuff we've already done. So bear with me here. Okay, so in part A, they're saying use the recent result from the Census Bureau. 66% of adults buy clothing online. And then in part B, we're going to assume that we have no prior information suggesting a possible value of the proportion. So we're going to solve this problem two ways. We're going to do it one where we have that information that 66% of adults buy clothing online, and that 66% is really our p-hat. That's our, if you think about success and failure for buying clothes online, 66% of adults buy clothing online, so that's going to be our p-hat. But then in part B, we're going to assume we don't have that information. And that's where some of those equations that we just looked at are going to come into play. So let's do these calculations out. Okay, so for part A, like we said, our p-hat is going to be 0.66. So to find our q-hat, we're going to do 1 minus our p-hat. So that's going to give us a 0.34 for our q. Does that make sense to everybody?
Mm.
Yeah.
Okay.
Yeah.
All right. Now we're told that we want to be 95% confident. So when we go back to our table, where is it? Back so far. Okay. When we go to our table for 95%, we're going to see that our critical value is 1.96. Okay, great. So we have that. Okay, so that's where this came from. Now, E. How did they get that 0.03? Any ideas of where that 0.03 came from based on the problem on the previous slide?
Because of the 3 percentage point? No more than 3 percentage points?
Yeah. So when that 3 percentage points, so basically they're telling you that your error can't be any greater than 3 percentage points. And that error is the same thing as that E. Now, previously we had calculated the E. Here we're being told our E. We're being told that our E is 0.003, which is the equivalent to 3 percentage points. If you were to take 3% and divide it by 100, that's where they're getting this number, that 0.03. Okay?
Mm-hmm.
So here we're not going to calculate an E. Our E was actually given to us. So now we're just going to plug everything in. 1.96 is our critical value squared times P, which was 0.66, times Q, which is 0.34, all divided by E squared, and we said our E is 0.03 squared. And when we do out that math, and I know people are gonna calculate, so feel free, but you wind up getting 957.839 people, basically, that you'd have to sample. Now, like we said, we're going to round up to the next closest person. So in this case, it's going to be 958 people that we would sample. Let me know when you guys are feeling good on this slide, and then we'll do part B.
Got it. Don't know how, but I did.
Okay. You don't know how. You can do it.
Don't.
It's a
You can
miracle.
do it. It's not a miracle. You're fine. Okay. Is anybody still working on the calculation?
I'm good.
Okay.
I'm just
Yeah, it's hard. It's hard in the online class to tell whether like people are like still working or not. So bear with me. Okay, so that's part A. Pretty straightforward, right? We just plug everything in from the original problem that we were given. Now, if we go back to part B, in this case, we're going to assume we have no prior information suggesting a possible value. So we don't have a p-hat. We don't know this 66%. The only thing we know is still 95% and that we want our margin of error to be no more than 3 percentage points. Those are the only two things we still know. So this is what our equation would look like for part B when we don't have that information. Our z is still going to be 1.96 and our e is still going to be 0.03 because we still are basing it on 3 percentage points of error. But here, rather than having that p and q to plug in, the equation gives us 0.25. Now, I don't want to spend a ton of time trying to talk you through where that 0.25 comes from, but basically what it is it's an estimate of what p and q would be in the real world. So that's where that 0.25 comes from. And that will always be the case. You'll always use 0.25 in that type of equation. And we saw that on that equation sheet. That 0.25 is actually baked right in there. So you don't have to worry about where it comes from or how you calculated it. It's just part of the equation.
So we use that when the P and Q is not given?
Yes. Yep. So we're told in the problem for part B that we don't know this 66%. Here we're going to assume we don't have any prior information. So in that case, we can't determine a P and a Q. So that's when we have to use this secondary equation, which plugs in 0.25 in place of that P and Q for us.
Okay.
So here, what we're going to see when we do this calculation out is that we get 1,067 people and change. Again, even though normally for 0.1 we wouldn't round up, because this is sample size that we're determining, we are going to round up. So we're going to round up to 1,068 people. So basically, when you compare the two, when we have the exact numbers for P and Q, we only need to survey 958 people. But when we don't have that information, we have to bump up the number of people that we're going to survey in order to ensure that the results are still valid to 1,068 people. And that kind of makes sense because here we don't have any of that prior information. And so we basically have to err on the side of caution and sample more people just to make sure that the results are going to give us a good, that we're going to have a big enough sample size. Okay. How are people doing on this one? Was everybody able to, I mean, I know the calculation isn't super difficult in this one, but was everybody able to see where they're getting their numbers and how they're plugging them in?
Mm-hmm.
Okay.
Yep.
Good. Okay. And then this last slide, so that's all that you need to know for determining a sample size. That's it. Not too bad. So far we've learned how to calculate a confidence interval. We learned how to determine sample size, and this last little part here, you probably really won't need this unless in somewhere in Math Lab they ask for it for you to do a point estimate like this. But I just want to show you real quick how to do this. So basically, once you have a confidence interval, so that was what we did back here, where we came up with this 0.828 being our minimum value, basically, of the possible values for our population, and this 0.8728 being the max, or 0.872 rather, being the maximum. you can use that if needed to calculate a point estimate. And how you do that is you take that upper limit, so that 0.872 that we got, and add it to that lower limit. I'm not sure what that was off the top of my head, 8.2 something, and divide by 2. And if you wanted to calculate or estimate a margin of error, the only difference there is you subtract them from one another and divide by 2. But for the most part, you're not going to deal with those two circumstances. They give you the equations here for how to do them. So if you see that in Math Lab, just note down these two equations for yourself. So if they ask this, you'll know how to calculate it. But it's not really something that's that helpful, which is why, it's not used as commonly as the other calculations that we saw. And that's why they don't spend a lot of time on it here. And that's the end. Yay! You can see that if we covered 7.3, which also has 40 slides, that this takes quite some time to get through all of this.
I imagine. It's a lot.
Yeah, basically what 7.3 is rather than estimating a population proportion, you actually estimate a population mean. So it's kind of similar material, but the equations are different and there is some differences between them. So I think that it's better to probably just leave things here so that we don't have to, you guys don't have double this amount of information in one sitting.
Yeah, because it would just confuse us, I'm sure.
Yeah, it's just going to make things more confusing. As you can see, this chapter is already confusing enough, let alone adding in more complexity to it.
That's for sure.
So this is what I propose. I propose that we take a little bit of a break so everybody can get up, stretch, grab a cup of coffee if they want to, and let's meet back up in 15 minutes, so 5 after 10. And we'll spend the rest of the time, and we can dive into some of the homework problems for this section.
Okay.
Does that sound good?
Okay.
Sounds good.
All right, sounds good. Well, then I'll see everybody in 15 minutes.
Okay.
All right. There I am. Hello. Okay.
Hi, Stacy.
Hello.
It's Nicole.
How are you? Don't mind me. Eating.
No, it's fine. Would I be able to get till next week to do chapter 6 quiz too?
What was the question?
If I can have till next week to do chapter 6 quiz.
Yeah, I emailed you and I extended it.
Oh, you did?
Mhm.
Oh, I didn't get it. Okay.
Oh no?
No,
Maybe I thought I emailed you.
I hope so. If not, it's okay.
Mhm.
So,
So Stacey, I missed like
Florida, my
half
best
hour of
friend's
the class.
Hold on. What?
I couldn't like log into Google Hangout at first, so I missed like the first portion. Did you go over anything I should know?
I'm actually recording the session
Okay.
because there were a couple people that weren't able to be here this morning. So what I'm gonna do is I'll put that up. And so, when did you come in?
At 8:30, I was logging under a different email. So
Oh, okay. What was the first part of the material that what were we talking
you were
about?
talking about the P hat.
Okay, so we had kind of just gotten started
Okay.
then. And so you shouldn't have missed much at that point. But like I said, I will post the video of this morning as well. So
Okay.
so if you want, you can just watch the beginning and just see if there was anything else you missed.
Okay.
Sorry about that.
It's okay. I was so confused. I emailed you twice. I was like freaking out.
I just saw the emails.
Yeah.
So sorry.
It's okay.
All right.
Maria.
There she is.
I think again. I don't know this computer. I think it's my internet down here. Everybody's frozen.
Oh no.
Some people are fixing their hair, and I see them like this. That was actually Erica. I was like, your hands are in the air, Erica.
Oh,
I
dear.
sent her a picture of herself.
That's funny. That's funny. Did it unfreeze?
And then I forget what her name is. The girl right now, her profile picture's up. She was eating
Nicole?
cereal, and then at one point, she was like this with the spoon in her mouth. It was so funny. I don't know what it is. I think it might be my internet. Everybody comes frozen on my picture down here below.
Oh, no.
Frozen.
Well, that's okay. It's okay.
So I actually have a question.
Sure.
So we just finished chapter 7.
Yep.
And we're going to review on that last class. However, if I want to review and I would like to get the final done.
Okay.
Because then when do we have to finish that final, that Sunday night?
Well, that's one of the things that they still haven't told me exactly when grades are due.
Okay.
And so that I was going to try to give you a little more time, but I need to know when the grades are due in order to be able to do that. And unfortunately, I don't. And so because of that, it's a little bit tricky. But that being said, let me think.
Because the week we're off for Memorial Week, I'd like to just study, go through everything, watch all the tutorials, and then just take that.
Exactly.
Yeah, no, that makes sense.
Is that okay?
Yeah, I mean, you could take the final whenever you want to. It certainly isn't something that you have to wait until that week. I'm just offering that up as a review because I know some people, but the other thing is I think that the final, let me see. Hold on a second.
See, my problem is when I start studying and reviewing it, I have to do it Like when I take the quiz, I have to do the homework and take the quiz because it's all fresh in my head.
Understood.
Oh, yeah.
Like, so when I finish class with you, and then if I don't touch it till Wednesday when I'm meeting with my tutor, I totally forget what we've talked about. But I notice that when I finish class and I go right to doing the homework right on the quiz, I'm actually a little afraid to take that final because I'm not going to remember everything.
Let's see. Well, one thing I'm just looking at the settings right now for the final. So you have 2 attempts at the final, just so you know. So you actually have the ability to go back. And I will also enable the ability to save for later. That way you can start and stop.
You know what? You enabled that with the quiz, but I haven't seen that with the quiz.
Weird. It's all enabled. I don't know why it wouldn't be letting you do it.
Once you're done with the
answer a question, and then it's down in the bottom left.
Down at the bottom?
Yes, down in the bottom left, you have to answer the question first and then save before you go on to the next one.
Yeah.
Okay. All right, thank you.
Yeah, I didn't see it at first either.
Okay. One thing to keep in mind, if you are going to do the final early, I have not yet altered the final. So I still need to go through the final and alter out a couple of sections to take out a few things.
If you don't mind letting us know once that's complete, and then I will definitely not touch it. I didn't touch it. Well, of course I didn't touch it. I didn't even.
Nope, nobody touched it. I can tell nobody touched it.
I would not touch it, so.
Well, yeah, I appreciate that. It's just a pain. Yeah, and the chapter 3 quiz will be closing in a few days because I extended it a little bit. So as soon as that's closed, I'll fix that one as well. And I also extended the chapter 6 quiz until next Saturday.
Oh, awesome.
So you have a little more time on that as well if you need it.
Yeah, thank you.
Good.
Okay. What about the chapter 5 one? Do people want the same extension from 6? All right, let me go and change that right now. Can you guys see my screen?
I did not do so good.
Okay. Can you guys see my screen right now?
Yeah.
Okay.
Yeah.
Yeah. All right. I wasn't sure if you guys could see what I was doing. But yeah, all it is for me is that. And then I'm done. Dude. Okay. All right, so 5 and 6 now are due next Saturday, so that gives you a little more time, and 7 isn't due until the last class.
Okay.
So that should help a little bit. And like I said, if I find that I have a little more time on the final, I'll certainly give you guys the benefit of it because there's not really anything I have to physically grade.
Yeah.
But I just don't know yet. They haven't sent me the memo saying this is when your grades are due for this section. I expect I'll be getting that memo though this week. Usually it's about 2 weeks before the class ends.
Okay.
Okay. All right.
Yeah.
So let's play around with some examples here because I think that would be helpful. So let's jump into chapter 7 here, and we can do like a little preview and look at some of the questions. All right.
Okay.
All right. So we'll do some of these together, and then we can kind of, I could take any questions, and then we'll just kind of wrap up. If we don't go all the way till 11, that's fine. Whenever it makes sense. So, okay. So
are we doing 7.3?
No, we are not going to do 7.3, and I've already taken it out of the homework and the quiz.
Oh, so we're just doing 7.2 then?
Yes.
Oh, okay.
Because 7.2 and 3 are each 40 slides apiece, it's just a lot to get through without making your heads explode. So,
Thank you so much.
So because of that, I pared it back, and I decided that we would cover 7.2 and that I would take out 7.3.
Okay.
Okay. So let's look at this first question here. So a newspaper provided a snapshot illustrating poll results from 1,910 professionals who interviewed job applicants. The illustration showed that 26% of them said the biggest interview turnoff is that the applicant did not make an effort to learn about the job or the company. The margin of error was given as plus or minus 3 percentage points. Okay, then they want to know what important feature of the poll were we not told. Okay, so let's look at this. So basically, they're wanting us to say, what information should we have been given here that we weren't if we really were going to make a determination? So the first option they said is sample size. So were we given the sample size in the problem?
Yes.
Yes. So it's not that. Okay. A confidence level. Let's see. All right. So the confidence level would be where they're telling us that we have like 95% confidence, whatever that may be. Now, do we see that at all in the problem?
Is it the 26%?
No, that's actually going to be your p-hat.
Oh.
I would think. So I don't think that they've given us a confidence level here. And that confidence level would be needed to figure out this margin of error. So let's see. The confidence interval, they gave us a little bit of info. Point estimate. It's kind of a weird question. I think it's going to be confidence. I know. This is my math lab. Yay. I think it's going to be confidence level. Yep. Okay. Yeah, so they didn't give us this at all in the problem, and you would need that if you were going to actually go about solving this kind of problem. So it's always important in a poll. If you go back to the slides that it was towards the end of 7.2 where we talked about polls, and the confidence level is a critical thing that has to be given in a poll. Because without that, you have to assume, you don't know whether it's a 95% confidence, a 90%, a 99. By default, you usually assume 95%, but here they didn't give us any indication, so that's what's missing. Okay. Let's see what else they're throwing at us here. Oh. Okay. This is actually a good one to cover because they haven't really they didn't really talk about this too much in the slides. So one of the things that you can do when you have a confidence interval, so normally a confidence interval is expressed like this, where you have like your population proportion in the middle, and then you have your lower limit and your upper limit listed. But the other format that it can be listed at is as p hat plus or minus e equals those two things. So one would just go on the end, and one would just go at the top. Because it's going to be minus 0.44 and plus 0.88 is basically how that's read. So this is just a different notation. But they didn't really talk about this at all in the slides, so I'm glad that we're seeing it here because you will, I guess, see this. So when they show it like this, they're basically just asking you to plug in those numbers from up top, but into just a different way of expressing it. That's all. So, oh, I see. Oh, okay. I see what they want. All right. So let me back up here. Actually, we'll leave this little part up because we're going to need it. So how I was doing it, you could also see, but this is actually a little different what they're asking for here. They're saying p hat goes in this spot where I have this 0.444, and e is actually going to go in this second spot. And that's where those last two equations that we saw on the slides come into play. So the first thing we have to do is calculate this p hat. And we're going to do that by taking our upper confidence limit, this 0.888, and adding our lower confidence interval limit, which is the 0.444, and then we're going to divide by 2. So let's all go ahead and do that. So our upper limit, again, is 0.888 plus our lower limit, which is 0.444. And then divide by 2. Let me know what you come up with.
0.666.
Yep, that's what I got.
That's what I got too.
Okay, so I'm going to jot that down. Now we have to do the opposite. To get our E, which is what we're going to put over here, we're going to take our upper limit, which is 0.888, and subtract our lower limit and divide by 2. So let's do that one as well. Minus 0.444 divided by 2. So let me know when you get that one.
So I'm a little confused.
Okay.
So the upper, express the confidence interval. So what is the upper confidence limit?
It's the higher side of this. So this is your interval here. So you have a low end to the left, and your upper end to the right.
So then that plus that divided by 2.
Yep.
Okay.
So this, the 0.888 minus 0.444 divided by 2 is going to give us our E.
Nice.
Okay. Okay.
2. Does that give us the same answer?
Nope.
No, sure, I did it wrong. Okay,
0.222.
Yep, that's what I got.
Okay.
So the 0.666 would go in the first box, and then the 0.222 would go in the second box.
Yes.
Ah,
So I'm going to plug those in. Because they're basically telling us that they want it as p hat plus or minus E. So when we did those little calculations, that's what we calculated, was our p hat and our E.
0.222.
Oh. Yep. Okay, so let's try checking that answer. Yay! Okay. Not so bad. But I'm glad we're going over some of this so that it's not confusing to you guys when you guys are getting in here.
Stacy, quick before you move on.
Yeah.
For the bottom half, the margin of error, what numbers did you take to subtract it? I'm sorry. There was some.
It's just these two numbers, your 0.888 minus your 0.444.
Oh, okay, so the same ones. Okay.
Same numbers.
Thank you.
No problem. All right.
but when I put in the 666, do I have to put the 0 first? Because I put the numbers in and got it wrong.
It shouldn't matter whether you put the 0 or you just put a point.
Right, because that didn't matter. I
It
got
shouldn't
the
matter.
666. So and the 666 goes in the first box, right?
Yes.
I'm getting it wrong.
Ursula, are you in the homework?
Yes.
Yep, it's the homework.
I don't know.
And the second box was the 222.
Yep.
Do you have different numbers than she does? They're all different for us.
Yeah, they're probably gonna be slightly different because
doing
they mix it up. I'm just showing you how to do the problem. It doesn't mean that you're gonna have the exact same numbers.
Okay, got it.
So you may have to you're gonna have to look at whatever they're giving you for numbers, but the way it's calculated is the same way.
Right, okay. I got those.
All right, let me know when we're ready.
I'm ready.
Okay.
Good.
All right. So here's where what I thought that they were asking us to do. So I apologize, but this one's actually helpful too because this is the one that we actually really need here. Okay. So this is what they've given us here is they're giving us a confidence interval. They're telling us the lower end of the confidence interval is 0.056 and the upper end is 0.118. And they want us to plug that in so that you wind up with the lower end here, like what we saw before, and the upper end over here. So all we're going to do is take those numbers from above and plug them in. So our 0.056 is going to go on this side because it's the lower of the two numbers. And the 0.118 is going to go on this side because it's the upper of the two numbers. And that's going to give us our confidence interval range. So you may have different numbers, but they're always going to be given to you the lower number first and the upper number second. And so these aren't really even so much calculations you're having to do, but just making sure that you understand what a confidence interval is what they're kind of getting at here. All right.
I have a question. That lower the number.
Yep.
Oh, you know what? I'm sorry. I read that wrong.
I know.
I see it.
Sometimes in decimals,
I see it.
it's confusing because you're like, oh, which is the lower number? Like, you know, like it can be a little confusing because it almost looks like this is bigger than this, but it's not.
Yeah. Yeah.
Yeah. So just be careful when you're dealing with the decimals.
My son just walked in and walked out. He started laughing. He just graduated. He just graduated college. That's why he's laughing at me.
Oh, he's done this already.
Yeah.
He's going, ha ha, Mom, your turn.
Yeah. And my daughter the same way.
Oh dear.
Yep.
Okay. All right, let's see if we can get there a few more. Let's see here. All right. Let's see what we got here. All right. So this is the fourth problem in the homework, and it says use the sample data and confidence level given below to complete parts A through D. Okay. So a Research Institute poll asked respondents if they acted to annoy a bad driver. Okay, that's kind of an odd way to put that, but
that is odd.
Okay, whatever. All right, so we're told that in the poll, our N, all right, so our N is 2,699 people, and our X, which in this case they're saying is 1,028, are the people who said that they honked. So that's actually going to be our P hat, which is why I don't know why they've labeled it as an X.
Because they like to confuse us.
I know they do. I know they do.
That's
it's
why.
So much fun to confuse you all.
Yeah.
But do people see what I'm saying? That that's really your P hat?
Mm-hmm.
Okay.
So what's the P?
The X.
Hat?
The P hat here, I believe, is going to be that what they're calling that X of 1,028. Because, again, all outcomes have to be classified as success or failure. So in this case, they're acting, did they honk to annoy somebody or didn't they? So 1,028 said that they honked. Oh, I see. Hold on. I lied. That 1,028 isn't going to be our P hat. We're going to figure out our P hat based on it, though.
So see how they're confusing the teacher. Can you imagine how we feel?
Yeah, no. So what they're telling us is that out of 2,699 people, 1,028 of them honked. So we need to figure out P hat based on that. And then we're going to use a 99% confidence interval. Okay, so let's start here. So the first things first is we got to figure out our P hat. So here they haven't given us our p hat, but we're given a proportion. We're told that 1,028 out of 2,699 people honked. So when we divide 1,028 by 2,699, we get our p hat, which is 0.38.
0.38.
Yep. But do try the calculation for yourself, because I want to make sure that you've got it. So your basically it's going to be x divided by n. That's what you're doing. So 1,028 divided by 2,699.
0.38.
Yep, 0.38. So that's our p hat.
Got it.
Okay.
All right. So part A is saying find the best point estimate of the population proportion P. So what is the best point estimate of that of the population proportion?
Oh, is that when we go to the table? No.
Nope, you don't need a table. This was on like the first couple of slides in chapter 7.
Okay.
Okay, find the best point estimate of population.
I'm sorry, I don't have those.
Oh, no problem. Let me I'll
Look
probably
here.
pull it up. Here, let's see. I'll pull it up on my side so you can see it.
I'm going to go into models and pull it up.
All right, right.
0.38.
Right here. This slide. So it's slide 5 in 7.2.
Wouldn't it be the p hat then?
Yeah, it's p hat.
So point.
So
0.38.
Yep. So it's not a trick question, but it sort of feels that way a little bit. All right. So let's jump over here and let's plug in our 0.38.
What slide was that again?
Oh, it wants 3 decimal places.
Slide 5.
Slide 5.
What?
Yeah, I got the wrong answer too.
Wouldn't it be 0.381?
I don't know.
I didn't think so.
Why is it? Why though?
Oh wow, I had to do 3.
Because it's 0.3808.
Ah,
round it
you're
to
right. You're right. You're right.
Okay.
Okay, I'm like, am I losing my mind?
Yeah, I had to do 3 decimal points. Okay.
Sorry,
Okay.
I missed the 3 decimal place part when I was doing that. See, it's really easy to get tripped up, even as an instructor. So I make the same mistakes that you guys do.
Is that the one where we take 1028 divided by 2699 and coming up with the 0.38?
Yes.
Okay, so we just have to keep 381. Okay.
Yeah, that's all.
Okay.
Okay. So the next step is we are going to calculate our margin of error. And that is, let's see, let's get our equation for margin of error up here. So that was this equation here, which is z equals the critical value, which is that modified z, times the square root of p hat times q hat divided by n. All right, so let's go back to the problem and let's find our numbers here. So our critical value, that's the first thing we need to find. So what were we given in the problem that we can use to help us find our critical value?
The critical value is that ZA divided by 2 symbol.
Yes.
Okay, so 99%.
Yep, so we're told that we have a 99%, oh, that's not what I want. A 99% confidence level is what we're looking at. So we're going to consult this table and find our critical value. So our critical value here is going to be 2.575. Okay, so we've got that. Now we've already figured out our p hat. and our N. We already have those from before. So what's our Q hat?
1 minus 0.381.
Okay, 1 minus 0.381. So let me get back to the problem here. Hold on. Okay, so 1 minus 0.381. So that's going to be 0.381. So our Q hat is going to be 0.619. Everybody see how I got that?
Okay, got it.
Okay, so now we're going to plug all those numbers in. So we're going to have E equals 2.575 multiplied by the square root of P hat, which is 0.381, times Q hat, which is 0.619, all divided by N, which is 2699.
Can you say that again?
Yep. So E equals the critical value, which is 2.575, multiplied by the square root of P hat, which is 0.381, times Q hat, which is 0.619, all divided by N, which is 2699.
I have a question.
Yep.
So I got to the problem E equals 2.575, and then the square root of everything is 0.00934. Do I multiply those two numbers?
Yeah, let me confirm your numbers real quick.
Okay.
I'm doing that right now. Using my husband's calculator, and I hate this calculator. I should just go get mine. What did you wind up getting for a number, Jillian?
I got 0.00934.
Yes.
So I multiplied that by 2.575.
Yes.
Okay, and that's the answer of E.
Yes. I came out with a final answer of 0.0241.
Yep.
Yes. Yes.
Okay.
Thank God.
All right, so let's plug that in and let's see how it goes.
Well, those aren't my numbers in my equation, so.
No, I understand. Okay, good. All right, so we calculated our margin of error. All right, so now we're going to construct our confidence interval.
Oh, God.
All right, it's not that bad. So we're going to take P hat, which is 0.381, and we're going to add our margin of error to it, 0.0241.
So say that again. P hat.
P hat plus the margin of error. So 0.381, which was our P hat, plus our margin of error, which is 0.0241. And that's going to give us our upper limit and I got 0.4051.
I do too.
Okay,
Yeah.
so that's what's going to go here. So 0.405. Okay, they only want 3 decimal places here. So I'll just do it like that. Okay, then we're going to do the same thing, but instead subtract. So 0.381 minus 0.0241.
So 0.381 minus 0.0241.
Yes. Yep. And there I get 0.35, rounding to 3 decimal places, 7.
Yep.
So 0.357. Okay? Yay. So the confidence interval is really the easiest part. The harder part is figuring out all the other stuff. I mean, really,
Yeah.
the confidence interval itself is pretty easy. Okay. All right. So now they want us to pick the correct statement that best describes what we just did. So let's look. So there is a 99% chance that the true value of the population proportion will fall between the lower bound and the upper bound. Yeah, well, in this case, one of the hard things is that in this case the answer is A. So all the other ones, I mean, I can read them and I can explain to you why they're not correct. So A is the correct answer, but then I'll walk through the other ones and I'll tell you why they're. Oh. What? Confidence level is the probability. What? All right. Fine. Why is that?
That's how we feel. What?
All right. It's got to be C then. Let me see. Okay. All right. So let me walk you through the other options and why they're wrong. So the first option A is there's a 99% that the true value of the population proportion will fall between the lower bound and the upper bound. The reason why they don't like that one is that one's saying that there's a 99% chance, and chance is not what we're dealing with here. We're dealing with confidence. So that's why A is wrong.
Oh.
B is wrong for the same thing. That one says 99% of sample proportions. That's not right either. We're not dealing with 90. The 99% is only confidence. So that's wrong. C is the correct answer. D is wrong because it says one has 99% confidence that the sample proportion is equal to the population proportion. That is not what the confidence interval tells us at all. The confidence interval doesn't deal with that relationship. The confidence interval gives us the range in which the true population proportion should fall. So these are a little tricky, but the correct answer is C. All right, how are people feeling about this one?
Okay.
Okay. All right. Let's see.
Yeah, okay.
Okay. All right. This one's a reading question. Let me see if there's any more real math ones. No, the rest are all non-math problems.
Good.
Which is good. Well, I guess there's a couple that aren't, but they're kind of the same things that we've been doing. Constructing a confidence interval, that kind of thing. All right. I think that's probably enough to get you guys started. I'm sure you guys will probably have some other questions, but I think that that's probably enough to at least get you through the homework and so that you can feel, ready to do the quiz. If questions come up during the week and as you're doing these, and we can go over more of them tomorrow. So tomorrow's Google Hangout, we can talk about any subjects you guys want. We can talk about stuff from 5 and 6. We can talk about stuff from 7. So just bring your questions, and we will cover kind of whatever you guys want to cover during that time.
Okay.
All right.
Thank you so much. Thank you.
Oh, no,
Yeah,
you guys are
thank
welcome.
you.
You guys are welcome. And like I said, it looks like I was successfully able to record all of this. So I am going to try to upload it to YouTube and do that. Because it's such a long video, I don't know how the uploading is going to go, but I'm going to try. So we'll see.
Thank you, Stacy.
All right, you guys have a great day, and I will talk to you all. Oh, geez.
Here we go.
Oh,
Thanks.
okay, stop that.
Bye.
Goodbye.
Bye.